The morning fog hadn't lifted yet over the Rechlin test facility when Hauptmann Werner Baumbach first saw the aircraft that would shatter everything German aeronautical engineers thought they understood about bomber design. September 15th, 1943. The B-17F sat on the hard stand like a wounded giant, its olive-drab paint scheme still bearing the scars of the combat that had forced it down near Bremen 2 weeks earlier. Baumbach, chief test pilot for the Luftwaffe's technical air arsenal, had examined dozens of captured Allied aircraft during his career. British Lancasters with their geodetic construction, American B-24 Liberators with their high aspect ratio wings. Each aircraft had revealed insights into Allied manufacturing philosophy and tactical doctrine, but nothing had prepared him for what he was about to discover inside this flying fortress. The numbers on the clipboard told an impossible story. Empty weight, 5,700 kilograms. Normal, loaded weight, 14,000 kilograms. Maximum takeoff weight, 29,000 kilograms. Baumbach read the figures twice, certain there must be an error. This bomber carried more than 12 tons of armor, self-sealing fuel tank material, and protective equipment. 12 tons. For context, an entire Messerschmitt Bf 109 G6 fighter weighed only 3,000 kilograms fully loaded. This single American bomber carried the equivalent weight of 4 German fighters solely in protection systems. The mathematical implications were staggering. Every kilogram dedicated to armor was a kilogram that couldn't be used for fuel, weapons, or structural lightness that German designers prized above all else. Yet here was an aircraft that had crossed the Atlantic Ocean, bombed German cities repeatedly, and survived sustained attacks from Luftwaffe fighters while carrying a protection burden that should have made it too heavy to fly. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The journey of this particular B-17F to Rechlin had begun 3 months earlier in a Boeing factory in Seattle, Washington. Production number 42-3, 0177, rolled off the assembly line on June 11, 1943, one of nearly 13,000 flying fortresses that Boeing, Douglas, and Lockheed Vega would eventually produce. The aircraft spent 6 weeks undergoing modifications and systems checks before assignment to the 381st Bombardment Group stationed at Ridgewell, England. The crew that flew her across the Atlantic in early August included pilot 2nd Lieutenant James Meredith, co-pilot 2nd Lieutenant Robert Walsh, navigator 2nd Lieutenant Thomas Brennan, bombardier 2nd Lieutenant Carl Fisher, and 6 enlisted crew members manning guns and technical positions. They named her Liberty Belle after Meredith's wife Elizabeth, painting the name below the pilots, a window in white script. Liberty Belle flew her first combat mission on August 19th, targeting the ball-bearing factories at Schweinfurt. The mission briefing had been sobering. Intelligence officers acknowledged that Schweinfurt was one of the most heavily defended targets in Germany, protected by massed flak batteries and stationed Luftwaffe fighter units specifically trained in bomber interception. The target's importance justified the risk. Schweinfurt produced over 40% of Germany's ball bearings, precision components essential for aircraft engines, tank transmissions, and virtually every weapons system the Wehrmacht fielded. Destroying the factories would cripple German war production for months. The cost would be measured in American crews who would not return. The 381st Bombardment Group contributed 16 B-17 seconds to the strike package that morning. Liberty Belle flew in the lead squadron's number 4 position, tucked into the formation where mutual defensive fire from neighbouring bombers would provide maximum protection. The formation crossed the English coast at 8:47 hours, climbing through scattered clouds toward operational altitude of 25,000 feet. Meredith's logbook entry for the mission noted routine conditions during the channel crossing and landfall over the Netherlands. Other groups reported sporadic flak over the Dutch coast, but no significant fighter opposition. The intelligence officer's prediction that Luftwaffe fighters were being conserved for defense of critical targets appeared accurate. The German fighters waited until the bomber stream approached Schweinfurt before launching their attack. At approximately 1300 hours, roughly 40 kilometers from the target, Meredith's tail gunner reported contacts at 6 o'clock high. Within seconds, every gunner in the formation was calling out fighter positions as Bf 109 seconds and FW 190 seconds dove through the bomber stream in coordinated attacks. The next 17 minutes would test every protective system that Boeing's engineers had built into the flying fortress. The first attacking fighter came from 12 o'clock high, a classic head-on pass that German pilots had perfected specifically to exploit bomber vulnerabilities. The Bf 109 G6 closed at a combined speed exceeding 600 km per hour, its nose-mounted 20mm cannon and cowl-mounted 13mm machine guns firing in sustained bursts. Meredith saw the muzzle flashes half a second before the rounds began impacting Liberty Belle's nose section. The bombardier's station, located in the aircraft's plexiglass nose, took the brunt of the attack. 20mm shells punched through the clear panels, exploding inside the cramped compartment where Lieutenant Fisher was hunched over his Norden bomb sight. The shells that should have killed Fisher instantly instead struck the armoured glass panel positioned directly in front of his position. The panel, measuring 24 inches wide and 18 inches tall, consisted of laminated bulletproof glass 3 inches thick, weighing 42 pounds. The 20mm shells starred the glass, cratering the surface and creating spiderweb fractures that obscured vision. But the panel held. Fisher felt the impact through the airframe and watched shell fragments ricochet off the protective glass inches from his face, but he remained uninjured at his station. Behind Fisher, shells continued through the nose compartment, striking structural members and equipment racks. Several rounds penetrated the forward pressure bulkhead, entering the cockpit area where Meredith and Walsh fought to maintain formation position. Here, the Boeing engineers' philosophy of comprehensive protection revealed itself in detail. The pilot and co-pilot seats featured armor plate backing, quarter-inch steel formed to protect the upper torso and head while allowing visibility and control access. Additional armor plates protected the seat's sides, creating a partial shell around each crew position. The floor beneath both seats incorporated armor plating that extended forward under the rudder pedals. Machine gun rounds struck Meredith's seat back with impacts he felt through the entire seat structure. The armor held, absorbing energy that would have killed him instantly. One round struck the headrest area, actually denting the steel plate before deflecting upward through the cockpit roof. Walsh's position took similar hits. A 13mm round struck the co-pilot's side armor panel at an oblique angle, the armor thick enough that the round deflected rather than penetrating, leaving a deep gouge in the steel but failing to pierce through. The German pilot broke off his attack run, diving beneath the formation while Meredith assessed the damage. His instrument panel showed multiple red warning lights. Hydraulic pressure was fluctuating. Oil pressure on number 3 engine was dropping. The interphone crackled with damage reports from crew positions throughout the aircraft. But everyone was still alive, still at their stations, and Liberty Belle was still flying in formation. The second attack came 30 seconds later from 3 o'clock high. 190 seconds in a coordinated slash attack, their wing-mounted cannons firing as they rolled through the formation. This time, the main target was Liberty Belle's midsection, where the wings joined the fuselage, and where 8 self-sealing fuel tanks held thousands of litres of high-octane aviation gasoline. The few W190's 20mm cannon shells walked across Liberty Belle's right wing, puncturing aluminum skin and striking internal structures. Several rounds hit fuel tanks directly. In an unprotected aircraft, these hits would have been catastrophic. Fuel would have poured from punctures, creating vapor clouds that any spark would ignite. The bomber would have exploded within seconds, taking all 10 crew members with it. Instead, Boeing's self-sealing fuel tank system demonstrated why American designers accepted the weight penalty of 3/4 of a ton per aircraft for this protection alone. Each fuel tank was constructed with multiple layers. The innermost layer was aluminum, providing structural integrity. Outside this sat a layer of vulcanized rubber, deliberately soft and pliable. Next came a layer of fabric mesh reinforcement. The outer layer consisted of additional rubber compound formulated to swell rapidly when exposed to aviation fuel. When the 20mm shells punctured Liberty Belle's fuel tanks, the fuel immediately contacted the rubber layers. Within seconds, the rubber compounds began swelling, expanding to fill the holes and seal against fuel loss. The system couldn't handle catastrophic damage from direct hits, but it could manage multiple bullet and shell fragment strikes without fuel loss or fire. Liberty Belle's tanks were holding, still feeding engines, despite taking hits that would have doomed an unprotected bomber. The attacks continued for 12 more minutes as the formation approached Schweinfurt. German fighters pressed their assaults with aggressive precision that reflected years of combat experience. They attacked from the sun when possible, using altitude advantage to build closing speed. They coordinated their runs to divide the gunners' attention, forcing the B-17 crews to engage multiple threats simultaneously. They focused on bombers that showed damage, recognizing wounded aircraft as easier targets. Liberty Belle took hits in every attack wave. Machine gun rounds stitched across the tail section. Cannon shells punched through the waist gunner positions. Shell fragments peppered the bomb bay doors and wing surfaces. The protective systems that seemed like excessive weight during design reviews at Boeing's Seattle facility now revealed their purpose under combat conditions that no peacetime test could replicate. The Ball turret gunner, Staff Sergeant Raymond Mitchell, experienced the armor protection's value most dramatically. A 20mm shell struck the turret's armored glass viewing panel, while Mitchell engaged an attacking W-190. The shell impacted directly in his line of sight, the explosion creating a brilliant flash that temporarily blinded him. When his vision cleared seconds later, Mitchell found himself staring at a starred, crazed glass panel that had absorbed the shell's energy. The armor glass had saved his life, stopping a round that would have decapitated him if it had penetrated. He continued firing at attacking fighters through the damaged but still intact glass, his turret still operational, despite the violent impact it had sustained. The bomb run itself lasted 4 minutes and 33 seconds, during which Liberty Belle and the other B-17 seconds maintained straight and level flight, while bombardiers guided their northern sights to release points. This was the most dangerous phase of any mission, the period when evasive maneuvers were impossible, and German fighters knew exactly where the bombers would be. Flak batteries surrounding Schweinfurt opened fire as the formation entered range, adding exploding 88mm shells to the maelstrom of fighter attacks. Liberty Belle shuddered from near misses, shell fragments clanging against aluminum skin like hail on a tin roof. Fischer, still at his damaged bombardier station despite the cracked armor glass in front of him, guided his bomb sight to the release point and toggled the bombs at 13:17 hours. 2 tons of high-explosive bombs dropped away, and Meredith immediately banked Liberty Belle into the formation's coordinated turn away from the target area. The bomber was still flying, still holding position, still combat effective despite damage that had left visible holes across every major surface. The flight home would take 2 hours and 40 minutes, every minute spent waiting to see if damaged systems would fail completely. Meredith's greatest concern was the hydraulic system. Pressure was holding at roughly 60% of normal, which meant landing gear extension might be problematic. The fuel situation worried him equally. He couldn't accurately measure fuel remaining with multiple tanks showing inconsistent readings, possibly from damage to sending units or from actual fuel loss. The self-sealing systems couldn't completely prevent. The interphone allowed crew members to report their status. The bombardier confirmed he was uninjured despite his position absorbing the heaviest attack. The Ball turret gunner reported his turret was still operational with damaged but functional armor glass. The waist gunners confirmed multiple hits to their positions, but the armor plates protecting gun positions had deflected rounds that would have caused casualties. The tail gunner reported his entire section was shot up, with controls responding sluggishly through damaged cables. Everyone was alive. In a bomber that had been under sustained attack for over 15 minutes, that represented a remarkable outcome attributable directly to the protective systems German engineers would soon study in disbelief. Liberty Belle crossed the English coast at 15:40 hours, descending toward Ridgewell with Meredith carefully nursing damaged systems. He ran through emergency procedures for hydraulic failure, preparing for the possibility of hand-cranking the landing gear down if normal extension failed. The tower had been alerted to their damage status, and emergency equipment was positioning along the runway. Meredith's landing gear concern proved well-founded. The normal extension sequence produced only partial deployment. The main gear indicator lights showed locked, but the nose gear remained retracted. Meredith and Walsh took turns working the emergency hand pump, a T-shaped handle requiring approximately 100 strokes to manually extend the gear through a backup mechanical system. After 15 minutes of exhausting pumping, the nose gear indicator flickered to green. The landing at 16:22 hours was controlled but rough, the damaged aircraft settling onto the runway with a thump that Meredith felt through the entire airframe. He stood on brakes that responded with only partial effectiveness, using rudder to keep Liberty Belle tracking straight as she rolled out. The bomber finally stopped with 500 feet of runway remaining, and Meredith shut down all 4 engines, listening to them wind down into silence that felt almost overwhelming after hours of continuous roar. The ground crew that swarmed Liberty Belle within minutes began counting damage even before the crew had fully exited. The preliminary report logged 93 separate combat damage points, including 21 cannon shell hits and 72 machine gun strikes. The armor glass in the bombardier's position had stopped 3 20mm shells. The pilot's seat armor showed 4 impact marks from machine gun rounds. The fuel tanks had sustained 14 hits, with all but 2 successfully sealed by the self-sealing systems. Every major surface showed damage, yet the aircraft had flown home, maintained formation, delivered its bombs on target, and brought all 10 crew members back alive. Liberty Belle never flew again. The accumulated damage was too extensive for field repair, and the aircraft was formally struck from 381st Bombardment Group's roster on August 23rd. But her combat career wasn't finished. Intelligence officers recognized the research value of an extensively damaged B-17 that had nevertheless survived. Within a week, Liberty Belle was being carefully prepared for transport to Wright Field in Ohio, where Army Air Forces engineers would conduct detailed analysis of every protective system's performance under actual combat conditions. The decision to preserve and study Liberty Belle reflected American military doctrine that treated combat-damaged aircraft as invaluable research data. Every hit, every penetration, every system failure provided information that could improve future designs or validate existing protection standards. The aircraft became, in effect, a full-scale test article that had undergone the most realistic trial possible, actual combat against a determined enemy using the most effective weapons available. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. But Liberty Belle's journey to become a research asset took an unexpected turn on September 2nd, 1943. The B-17F, being ferried to Wright Field via Iceland and Greenland, encountered navigation difficulties in deteriorating weather over the North Atlantic. Low on fuel and unable to determine position accurately, the pilot made the decision to divert to the nearest friendly airfield. What he didn't know was that rapidly changing weather patterns had pushed the aircraft farther east than calculated. The airfield he identified as friendly was actually Rechlin, Germany, and by the time the crew realized their error, German fighters were already forcing them down. The emergency landing at Rechlin was controlled but resulted in additional damage to the already battle-scarred bomber. The crew was captured immediately and spent the remainder of the war in prisoner camps. But Liberty Belle, now in German hands, was about to provide Luftwaffe engineers with their most complete look yet at American bomber protection philosophy. Hauptmann Werner Baumbach received the assignment to conduct the initial assessment on September 8th. His orders were explicit. Determine why this bomber had survived combat damage that should have destroyed it. Identify every protective system and measure its weight contribution. Assess whether German bombers could incorporate similar protection without compromising performance. The examination would take 3 weeks of intensive analysis and would ultimately produce a technical report that challenged fundamental assumptions underlying German bomber design. Baumbach began his inspection at the bombardier's station in the nose, where the armoured glass panel still bore the impact marks from 3 20mm cannon shells. He measured the panel carefully. 3 inches thick, 42 pounds, bulletproof glass, consisting of multiple laminated layers with plastic interlayers. German bombers used armoured glass in limited applications, primarily for pilot windscreens, but nothing approaching this thickness or weight. The standard German armoured glass was approximately 50 millimeters thick, roughly half the thickness of the American installation. The difference reflected divergent design philosophies. German engineers minimized armor protection to preserve aircraft performance, accepting higher crew casualties as an inevitable cost of maintaining speed and agility. American engineers maximized protection even at substantial weight cost, calculating that trained crews represented irreplaceable assets worth preserving through heavy defensive measures. Baumbach photographed the starred glass panel from multiple angles, documenting how the laminated construction had absorbed shell impacts without catastrophic failure. A single-piece glass panel of equivalent thickness would have shattered completely from the first hit. The laminated design, with its multiple layers and plastic interlayers, distributed impact energy across the entire panel, allowing it to absorb multiple hits while remaining partially functional. Moving aft into the cockpit area, Baumbach found armor protection that exceeded anything installed in German bombers by an order of magnitude. The pilot's seat featured a 1/4-inch steel plate backing that covered the entire seat back from shoulder height to below the seat cushion. The plate was contoured to follow the seat's shape, maximizing coverage while maintaining ergonomic access to controls. Additional side plates protected the pilot's flanks. The floor beneath the seat incorporated armor plating that extended forward under the rudder pedals. Similar protection surrounded the co-pilot's position. Baumbach's team removed one of the pilot's seat armor plates to weigh it precisely, 68 pounds for the main backplate alone. The complete armor protection for both pilot positions, including side plates and floor armor, totaled approximately 240 pounds. For comparison, the entire pilot protection system in a Heinkel He-111 bomber, Germany's primary medium bomber, consisted of a single 8mm armor plate behind the pilot's head, weighing perhaps 30 pounds. The disparity illustrated the fundamental difference in how the two air forces valued pilot survival versus aircraft performance. German doctrine emphasized building large numbers of aircraft quickly, accepting that pilots would suffer higher casualties but calculating that replacement pilots could be trained faster than replacement aircraft could be built. This calculation had proven correct during the war's early years, when Germany held the initiative and could afford steady attrition rates. But by 1943, the calculation was failing. German pilot training programs couldn't replace experienced crews lost over Germany and the Eastern Front. Meanwhile, American doctrine prioritized keeping experienced crews alive, reasoning that veteran pilots flying heavier aircraft would achieve better results than inexperienced pilots in lighter machines. The armor weight that German engineers considered excessive waste, American engineers considered essential investment in force effectiveness. Baumbach moved deeper into the fuselage, examining the fuel system that had kept Liberty Belle flying despite 14 hits to fuel tanks. The light B-17F carried 9 fuel tanks with total capacity of 2,700 gallons distributed throughout the wings and fuselage. Each tank employed self-sealing construction that added substantial weight but provided protection German fuel systems completely lacked. The self-sealing system's design revealed sophisticated engineering. The innermost layer consisted of standard aluminum fuel tank construction. Outside this sat a layer of untreated crude rubber, deliberately soft to maintain flexibility. Next came a layer of nylon fabric, providing structural reinforcement. The outermost layer used treated rubber compound formulated to swell rapidly upon contact with aviation gasoline. When bullets or shell fragments punctured the tank, fuel would immediately contact the rubber layers. The treated outer layer would begin swelling within seconds, expanding to fill the puncture. The untreated inner rubber layer provided additional sealing as it compressed against the treated layer. The nylon, fabric prevented the swelling rubber from tearing under pressure. The system added approximately £35 per tank, totaling over £300 for the complete fuel system. But the weight penalty purchased survival. Baumbach examined Liberty Belle's damaged tanks carefully, photographing holes where self-sealing compound had swollen to plug punctures. Several holes showed successful sealing around damage that would have caused catastrophic fuel loss in German bombers. 2 larger holes had not sealed completely, explaining the fuel loss Meredith had noted during the flight home. But even these larger punctures had been partially contained, slowing fuel loss enough that the bomber reached England. German bombers used standard aluminum fuel tanks with no self-sealing capability whatsoever. When hit, they leaked continuously until empty or until spark ignited fuel vapor and destroyed the aircraft. Luftwaffe crews called fuel tank hits Todesstoß, the death blow, because survival after fuel tank damage was extremely rare. German engineers had experimented with self-sealing systems as early as 1940, but the weight penalties were deemed unacceptable for aircraft that needed maximum performance and agility. The decision prioritized capability over survivability, exactly as Japanese engineers had done with the Betty bomber, and with similar results. German bomber losses to fire after fuel system damage ran catastrophically high throughout the war. The comparison was not lost on Baumbach. His report would note that American bombers routinely returned from missions with fuel system damage that would have destroyed German aircraft. The self-sealing tanks represented perhaps the single most effective survivability measure American designers had incorporated, providing protection that directly translated to completed missions and recovered crews. Moving through the waist gunner positions, Baumbach found additional armor installations protecting crew stations. Each waist gun position featured armor plating on 3 sides, creating a partial shell around the gunner while maintaining visibility and firing arcs. The armor plates were positioned to protect against attacks from the most likely threat vectors, German fighters attacking from the sides and rear. The plates measured approximately 8 mm thick, substantial enough to stop machine gun rounds and shell fragments, while remaining light enough that gunners could move freely. The ball turret, suspended beneath the fuselage, featured the most sophisticated armor protection Baumbach had yet encountered. The turret's spherical housing incorporated armored glass viewing panels 3 inches thick surrounding the gunner's position. The glass provided visibility while protecting against rounds coming from below, the turret's most exposed quarter. Additional armor plating protected the turret's mechanical systems and ammunition storage. The complete turret weighed over 1,000 pounds, with approximately 200 pounds dedicated solely to armor protection. German aircraft designers had never developed an equivalent to the Sperry ball turret. The closest German equivalent was the remotely operated ventral gun installations on some bomber variants, but these lacked the visibility, fire control effectiveness, and crew protection of the American design. The ball turret represented American willingness to accept substantial weight and complexity, penalties in exchange for tactical capability and crew survival. It was precisely the kind of elaborate, heavy installation that German doctrine rejected as incompatible with performance requirements. Baumbach's inspection of Liberty Belle's tail section revealed how comprehensively Boeing's engineers had approached crew protection. The tail gunner's position featured armor plating, protecting the gunner's back and sides. The armor extended from floor to overhead, creating an armored compartment that protects against rounds coming from behind, the tail gunner's most vulnerable quarter. Even the tail gunner's seat incorporated armor backing, adding protection during the long hours spent in that isolated position. The control systems showed redundancy that German aircraft lacked. Liberty Belle's control cables were routed through multiple paths, so damage to one cable set didn't eliminate control authority completely. The bomber had flown home despite severed cables, because backup routing provided degraded but functional control. German bombers typically used single cable runs for each control surface, meaning any cable damage potentially resulted in complete loss of that surface's control. After 3 weeks of intensive examination, Baumbach's team had catalogued every protective system and measured its weight contribution. The final accounting was sobering. Armour plating for crew positions totaled approximately 800 pounds. Self-sealing fuel tank systems added 320 pounds. Armoured glass installations contributed 215 pounds. Redundant control systems and protective equipment added another 600 pounds. The total protection burden exceeded 12 tons, as the initial figures had indicated. 12 tons dedicated solely to keeping crews alive and aircraft functional after sustaining battle damage. Baumbach's official report, completed on October 4, 1943 and classified Geheime Kommandosache, secret command matter, provided German aviation authorities with their most complete analysis yet of American bomber protection philosophy. The report's conclusions challenged fundamental assumptions that had guided German aircraft design since the war's beginning. American bombers carried protection systems weighing more than complete German fighters. The weight penalty was accepted deliberately as necessary cost for crew survival and mission effectiveness. Protected American bombers were demonstrating survival rates 3 to 4 times higher than unprotected German bombers in similar combat environments. The report's most significant conclusion addressed whether German bombers could incorporate similar protection without compromising performance. Baumbach's analysis was unequivocal. Adding 12 tons of protective systems to existing German bomber designs would reduce performance below acceptable thresholds. Maximum speed would decrease by approximately 15%, service ceiling would drop by roughly 3,000 meters, range would decrease by 20 to 30%. The performance degradation would make protected German bombers unable to fulfill their assigned missions. But the report also acknowledged the terrible cost of maintaining performance at the expense of protection. German bomber crews were suffering casualties that exceeded replacement rates. Experienced crews were being lost faster than training programs could replace them. The aircrew shortage was becoming as critical as aircraft production limitations. American forces were accepting weight penalties for protection, then compensating with larger engines, stronger structures, and greater industrial capacity to produce heavy but survivable bombers in massive numbers. The mathematical reality was inescapable. Germany couldn't match American industrial output. German factories would produce approximately 18,000 bombers during the entire war. American factories would produce over 97,000 heavy and medium bombers during the same period, each one carrying protection systems that German aircraft couldn't accommodate. The disparity in production meant that even if German aircraft achieved better individual performance, American numerical superiority would prove overwhelming. Baumbach's report circulated through Reichsluftfahrt Ministerium offices during October and November of 1943. The response revealed how deeply embedded the performance over protection philosophy had become in German aviation doctrine. Some officials dismissed the report's conclusions, arguing that German tactical doctrine emphasized speed and agility over brute survivability. Others acknowledged the protection disparity but maintained that Germany lacked the industrial capacity to build American-style heavy bombers, even if designers wanted to. A few recognized that American protection philosophy represented superior long-term strategy, but by late 1943, Germany had neither the resources nor the time to redesign its bomber fleet. The only tangible result of Baumbach's report was a directive issued in December 1943 requiring limited armor protection for pilot positions in new bomber designs. But the armor specifications remained minimal compared to American standards, 8mm plates behind pilot seats, rather than the comprehensive protection American crews received. Even this limited improvement was often deleted from production aircraft when weight needed to be reduced to meet performance targets. German bombers would fight the war's remainder with essentially the same vulnerable protection levels they'd carried since 1939. Meanwhile, American bomber protection continued improving based on combat damage analysis from aircraft like Liberty Belle. The B-17G model, introduced in late 1943, featured additional armor protection for vulnerable areas identified through damage reports. The chin turret added to defend against head-on attacks included armored glass and protective plating. Self-sealing fuel systems were refined to handle larger caliber damage. Redundant systems became even more comprehensive. Each improvement added weight, but operational analysis showed that protected bombers completed more missions, suffered fewer crew casualties, and required less replacement than lighter unprotected designs. The numbers validated American doctrine conclusively. By 1944, B-17 operational loss rates had decreased to approximately 4% per mission, despite intensifying German fighter opposition. German bomber loss rates during the same period exceeded 12% per mission over heavily defended targets. The threefold difference in survival rates correlated directly to protection system effectiveness. American crews were 3 times more likely to survive missions and return for additional combat operations, multiplying the effectiveness of training investments and building institutional experience that German forces couldn't match. Robert Johnson's P-47 had demonstrated fighter aircraft survivability. Liberty Belle demonstrated that the same philosophy applied to heavy bombers produced even more dramatic results. The 12 tons of armor, self-sealing tanks, and redundant systems weren't excessive engineering. They were precisely calibrated investment in force effectiveness, purchased with weight but repaid through crew survival and mission completion rates that justified every pound. The captured B-17F spent 19 months at Rechlin, undergoing additional testing beyond Baumbach's initial assessment. German test pilots flew the bomber when fuel could be obtained, experiencing firsthand the handling characteristics of an aircraft carrying 12 tons of protection equipment. Their reports uniformly noted that American bombers felt heavy and sluggish compared to German designs, exactly as theory predicted. But the reports also acknowledged that the bomber remained controllable and effective despite the weight burden, suggesting that American pilots were adapting to characteristics that German doctrine had rejected as unacceptable. Liberty Belle was destroyed during an Allied bombing raid on Rechlin in March 1945, consumed by fire during an attack on the very facility where she'd been studied. The irony was not lost on surviving German personnel. The bomber that had survived intense combat in August 1943, that had flown home despite catastrophic damage, that had demonstrated American protection philosophy to German engineers, was finally destroyed on the ground by bombs delivered from aircraft employing the same protection systems she'd exemplified. Hauptmann Werner Baumbach survived the war and became one of the few German aviation officers to write extensively about captured Allied aircraft examinations. In post-war interviews conducted during the 1950s, he spoke candidly about Liberty Belle's impact on his understanding of aircraft design philosophy. "We built aircraft to perform missions," Baumbach reflected. "The Americans built aircraft to bring crews home. In a short war, our approach would have succeeded. In a long war of attrition, their approach proved superior. We learned this lesson from examining that single B-17, but we learned it too late to change our own aircraft designs." The lesson extended beyond World War II into post-war aviation development. Modern military aircraft universally incorporate comprehensive crew protection as fundamental design requirement rather than optional addition. Armored cockpits, self-sealing fuel systems, redundant controls, ejection seats, all reflect the doctrine that trained crews represent assets more valuable than airframes. The philosophy traces directly to World War II American bomber design, vindicated by combat results that proved protection enhanced rather than diminished combat effectiveness. The B-17 Flying Fortress production totals tell the story in numbers that German planners couldn't match. 12,731 B-17 seconds were produced during the war years, each one carrying the 12 tons of protection that German engineers considered excessive. These bombers flew 291,000 sorties over Europe, dropping 640,000 tons of bombs, while suffering losses of approximately 4% per mission. The survival rate, directly attributable to comprehensive protection systems, meant that individual crews could complete 25 mission tours with reasonable survival probability. German bomber crews rarely survived 25 missions over comparable targets. The mathematics of protection versus performance resolved decisively in favor of protection when measured over sustained operations. Unprotected aircraft achieved marginally better performance on individual missions. Protected aircraft achieved dramatically better results across multiple missions because they survived to fly repeatedly. The compounding effect of survival meant that protected bomber forces grew more effective over time, while unprotected forces suffered attrition that degraded capability despite individual aircraft superiority. Liberty Belle's legacy lives in every modern military aircraft that prioritizes crew survival as primary design goal. The 12 tons of armor that shocked German engineers in September 1943 established the standard that all subsequent military aviation would follow. Protection isn't excessive weight. It's essential investment in the most valuable component of any weapons system, the trained human operator, whose survival determines whether expensive platforms deliver sustained combat value or become single-use assets consumed in their first engagement. The Flying Fortress earned its name through comprehensive protection that made it virtually impossible to destroy quickly. German fighters could damage B-17 seconds, could force them from formation, could kill individual crew members. But destroying a flying fortress required sustained attacks that few German fighters could deliver before escort fighters intervened. The protection philosophy built into every rivet and armor plate gave American crews the precious seconds they needed to fight back, maintain control, and reach friendly territory. Those seconds, purchased with 12 tons of protection equipment, made the difference between overwhelming losses and acceptable attrition rates. When German engineers examined Liberty Belle at Rechlin, they weren't just analyzing an enemy bomber. They were witnessing physical evidence of how industrial capacity enabled protection philosophies that Germany couldn't afford to adopt. American factories could build heavy bombers because American industry could produce the materials, engines, and components necessary to make heavy aircraft practical. German industry, strained by multi-front warfare and strategic bombing, couldn't match that capacity even if designers advocated for protected bombers. The 12 tons of armor in Liberty Belle represented not just engineering choices but industrial reality. Only a nation with effectively unlimited production capacity could afford to build bombers carrying 12 tons of non-mission essential weight. Only a military with secure logistics could fuel and maintain such heavy aircraft across thousands of missions. Only an air force with comprehensive training infrastructure could produce crews capable of flying protected bombers effectively, despite their weight and complexity. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.